Hello everybody, this is Emirhan. I'm a fresh PhD student in computer science. If you have a hard time understanding AI papers because of the heavy math behind them, I think you have stumbled upon the right video. Because in this video series, I will try to explain you 4 different math topics to better understand AI. The first one, which is this one, will be in information theory, and I will also explain some other overlapping concepts. In the second one, I will explain optimization, and the third one will be in linear algebra, and the fourth one will be in probability and statistics. And at the end of each video, I will try to explain the paper using the information I have given in the video. So yeah, let's start.
So let's start with what is information, right? So let's say you have a field, just like a rectangular here, and you have 2 different sections, and you're making an experiment throwing a stone. And if your stone has fallen here, would you be really surprised? Not much, because the probability was already 50% or 1/2, right? In a different scenario, let's say you have 4 different sections and it fell here, you would be more surprised. So the event occurring would give you more information, right? Let's say you have even more fields and the probability of it falling here is even lower, and the information you have would be even higher. So as you can see here, guys, there's an inverse correlation or inverse relationship between the information and the probability. So actually, the information is a quantity of how much the event surprises you, right? So the Shannon come up with this formula, and actually, let's say it is 1/2, the first example, if you remember. So 1/2 is 2 to the minus of -1, and -1 comes to the beginning. It's a property of logarithm, and the result would be 1 bit. If it is 1/4, the result would be 2 bits. Why? 1/4 is 2 to the minus of -2, and -2 comes into the beginning, so it would be +2, and then this is this is just 1. Logarithm 2 of 2 is 1. And if the probability is lower, the information is higher, as you can see here. So you would be surprised more, right? So entropy is just the expectation of information, or the average of information. Let's say there's an experiment, like you throw the penny like 10 times or 2 times, and the average information per event or per experiment is entropy. Okay, let me give you an example. You will understand even better. Let's say you're throwing a penny and it's either tails or heads, right? Or head and tails. So the probability of it occurring as a head is 0.5 or 1/2, and the probability the actual, the probability is 1/2. So when you take the average, it's 1 bit. I mean, just let's say you're throwing a penny and it's tails, right? It gives you 1 bit of information, if you look at it from here. And you throw another penny, or you throw the same penny again, and you complete the experiment. So again, the probability of it becoming heads or tails, again 1/2. So the average information is 1 bit. Nothing really crazy, right? But let's say the penny is not a usual penny and it's slightly different, and the probability of it coming up as tails is 0.9, let's say, and the head is 0.1. So even though this event, let's say it was 10% of the chance, but it occurred, it would give me a lot of information. But the probability of it happening is quite low, which is 0.1, right? So even though this gives me a lot of information, specifically like around 3 bits, the probability is so low that the entropy, even though the information is a lot, the entropy, the average of the whole experiment is not much, because most of the time, it's 90% of the time, let's say, tails comes up, or heads, I don't know. So this wouldn't give me enough information. This would give me so little information. I wouldn't be surprised at all. It was already 90%. Of course it would come up, right? So on average, you only have like 0.47 bits of information. As a quick reminder, expectation is the same as the average if you have a uniform distribution. But yeah, most of the time you have a Gaussian distribution, so they might not be the same. But yeah, this one over here, xi, would be 1 over n if all of the events have the same probability. Sorry, the p of x, I mean, it would be 1 over n if all of them has the same probability. So let's say there's only 2 events occurring in heads or tails, it would be 1 over 2, right? So it would be a uniform distribution, so they are the same. So for this one, for example, it's the same thing. So you might be already wondering what is cross entropy, because maybe when I told you entropy, if you worked with some AI models, or if you have ever trained a model, you probably used cross entropy. So in here, I will give you 3 different quantities or 3 different metrics: cross entropy, Child divergence, and TVD, which is total variance distance, or total variational distance. They are basically the same. So all of them, all 3 of them, are just trying to understand what is the difference of 2 different Gaussian distributions. Okay, so cross entropy is mostly used in loss functions in deep learning, right? So let's say this is the your model's prediction, and this is the actual true distribution. So there was a picture of a cat, but your model, which is Q, has guessed it as 0.7 of cat, 0.2 for dog, 0.1 for bird, right? So if here it's a good prediction, but let's say the prediction was 0.1 here, right? So if you put 0.1 over here, it would bump up, right? It would burst. And this one is just 1, so this value over here would be a lot. So your loss, your error would be a lot. But here, since it's 0.7, which is close to 1, if it's 1, it's 0, so you don't have any errors. But you have a small error here, since 0.7 is close enough to the 1. So yeah, cross entropy is just again trying to guess or trying to measure the difference of 2 different Gaussian distributions, and widely used in deep learning as a loss function. Okay, there's also something called Child divergence, and as I told you, it's basically the same thing: cross entropy, Child divergence, or total variational distance. They all measure the difference of 2 different Gaussian distributions. So as you can see here, there's a ratio also. It looks like entropy, but slightly different. Actually, it is the cross entropy minus the entropy of pi. So yeah, by the way, you can try to prove it by hand yourself. It's not that hard. Okay, as I told you, let's say this is P and this is Q, and you look at the ratio of them. You also like multiply it with the true distribution, or PX. And it's widely used in generative models or generative AI. If you know diffusion, if you know the image generating algorithms, right? They use Child divergence in their loss function, and variational autoencoders. Variational autoencoder is a part of diffusion, by the way. We can talk about them in a later video. But yeah, let's say you have the input and you have the output. You compress an image and then decompress it. You encode it and decode it, right? And you look at your like difference of your input and output, basically the same image. You're trying to perfectly compress it and open it, right? So you look at the difference of inputs and outputs with Child divergence in this setting. So as I told you, as a loss function, cross entropy is used, but in some generative models, Child divergence is used. There's one more thing, which is called TVD, or total variational distance. It's used in the paper I will present you in the end of the video. So basically the same thing. 2 different Gaussian distributions, and it's looking at their difference. Sometimes it's preferred over Child divergence or cross entropy, which we can also see in the paper I will tell you. So one reason is it's a symmetrical function, and it's in between 0 to 1. So for example, Child divergence doesn't have any boundaries, so it can be way more than 1. It can be 0 also, but it can be more than 1. This one is in between 1 to 0. The basic thing is because you take for any probability, the summation of that probability is 1, right? So it cannot be more than 1. And you look at the difference, so it's even less than 1. And if, let's say, the result is 0.5, it means P of x is 50% different than q of x. So yeah, let's go with the mutual information. Let's say we have x, y, and z, three different variables. And if the mutual information, this really like intimidating formula, if the mutual information of x and y are bigger than x and z, then we can say that y has more information about x than z. Why? Because the mutual information is higher, right? And don't get scared with this formula. It's basically the, it looks like the Kyle divergence formula. And it's actually the entropy. It's even similar to the entropy formula. And when you look at it, it's actually nothing more than entropy of x plus entropy of y minus the cross entropy of them. Okay. So yeah, that's it for the mutual information. And in the paper I will show you, we will compare the embedding models. I will tell you what an embedding model is, but maybe you already have some intuition that we can use mutual information in their comparison, right? Also, there's sufficiency, another basic concept in information theory. So basically, a statistic is a function of the data, let's say a mean of our data or our population, or a variance of our populations, something like that. And it's something computed from the data. The mean is computed from the data, right? Or the median value, for example, is computed from the data. And let's say the parameter theta, it's a property of the population, and we aim to estimate this, okay? And if a statistic is sufficient, it means the t of x of the statistic is enough to estimate the theta. So let's look at here, for example, p of x given tx and the parameter theta is exactly the same as p of x given t of x. So you don't even need the parameter because t of x, the statistic of the data, is enough to estimate the parameter, which is called sufficiency. It is sufficient, right? Let me give you a very basic example, which is sufficiency again. So yeah, let's say you already know the x hat or the average of the data, right? And let's say you have a data x1, x2 to the x2, xn, sampled from the normal distribution with a mean value of mu and a variance of sigma square. So let's say you already know the mean, as I told you, then you can already guess the mu, right? Because they are basically the same thing. So your statistic average is enough to estimate the parameter theta, which is mu in this case, let's say, is enough. You can already estimate the mu from this statistic t of x, right? So that's a very basic example, but just remember this part because in the paper we will derive from the sufficiency example, okay? Hello again, everybody. I wanted to continue my video in a more refreshing environment, and let's talk about Fourier transform. So Fourier transform is basically when you have a data in time domain and you want to convert it to the frequency domain so that you can explore naive identities of your data or your signal. For example, it's widely used in image compression, and I will explain you how. Okay, so let's say you have a voice record, right? Yeah, such a terrible drawing it will be, but still, let's say the y-axis is decibel, let's say, of your voice, and this is the time domain, and let's say your voice is something like this, okay? Then, after the Fourier transform or fast Fourier transform in computers, because Fourier transform is not really applicable in a computer environment, they use something more efficient, and they call it fast Fourier transform, but don't worry about it. After the Fourier transform, you will have something like this. So again, this is the frequency, let's say hertz, and this is the magnitude, okay? Magnitude of your frequency. So you would see something like this. So let's say in your voice record there are two different frequencies, right? So let's say you and your girlfriend at the same time are talking in your voice record. Then after the Fourier transform, you can see, for example, this one is probably your voice, because men's voice are most of the time, or my voice, let's say, most of the time has a lower frequency, and this is your girlfriend's or my girlfriend's voice, let's say. Okay, so Fourier transform is basically this. Okay, and let's see how it is used in image compression in the next part. Okay, so let's first start giving the formula of Fourier transform. So if it's a discrete Fourier transform, you use a sigma like this, but let's give the formula of the continuous Fourier transform. So it would be an integral, nothing so different, from minus infinity to infinity, let's say. And you have the data I already shown you, like the voice record, let's say in time domain, right, ft, and then you have an exponential function a minus jwt dt, and this is the formula for, so after you do that you converted your function, your signal, to the frequency domain. Okay, so yeah, what is w, by the way? Here it's the angular frequency, so which is basically 2p phi, 2pf, let's say. So f is the frequency. Okay, so nothing so different. So yeah, let's see how it works in images. Let me take another whiteboard. Okay, so let's say you have an image. Okay, you have an image of a face, let's say. Okay, not a very nice face though. You do the Fourier transform or FFT, let's say, but it's an image. It's not a voice record, so it's 2D-dimensional. So you don't do normal FFT or FT. You do two-dimensional FFT. It is actually just you process the rows, then the columns. It doesn't mean the order doesn't like affect. So either you start with doing the columns or the rows, no problem. But you do the two-dimensional FFT, okay? And then you have something like this. Let's say something like this, okay? Something like a flower. But most of the values in this flower is basically redundant, or you can compress some of them. You do something like entropy coding, something called entropy coding. Let's say, in a more basic terms, let's say, since most of them are, for example, these values are very close to the zero, right? You just prune them, you just make them zero, okay? And what you have after the entropy coding step is something like this, let's say, smaller flower, right? And then you have the inverse Fourier transform, again 2D, and then you have the image back. Okay, you have the image back. Okay, I just played with this image, but normally it was something like this. You lost some information, but still it is like you compress the image, right? So you don't need to waste a lot of memories thanks to that. So let's say this one was 2 megabytes and this is just 700 kilobytes, right? And information theory also explains how to not lose the information. So you can compress it without losing any information, and it comes from the entropy. I will tell you in a second. But to quickly summarize what happened, okay, you have the image, you did 2D Fourier transform, fast Fourier transform in computers. It's a more, as I said in the beginning, it's a more effective way of doing Fourier transform. Then you have something like a flower. You cancel out some values that are really close to the zero or really big, let's say, make them 1 instead of, like, let's say 2000 or 200. And then you do the inverse Fourier transform, and then you have the image back, right? And instead of saving this image, you save this image and save a lot of memories, right? By the way, it's most of the time not FFT, especially in JPEG compression. It's continuous, a discrete continuous transform, so DCT. But no problem, they have the same logic, just it takes the image and converts it to the frequency domain. So yeah, that's it. Hello again. So to clarify some points, in the first example I gave you, so let's again say you have a voice record, right? So the main purpose of doing Fourier transform is to see the different properties of your voice, right? Of your voice record in general, right? So we cannot say, just from looking at in time domain, we cannot say which one is your voice or which one is your girlfriend's voice. Decibel doesn't say much, because you can talk loudly and your decibel would be higher even if you're a girl or a boy, doesn't matter. Okay, so for example, this can be your voice, your voice, let's say Emirhan E. This can be girlfriend of Emirhan's voice, right? And this can again be my voice. But as I told you, since it has a lower frequency, it's probably my voice. And this is my girlfriend's voice, right? So when you convert them to the magnitude, to the frequency domain, it's more observable, right? And let's say there are like 100 voices. If each of the person has a different frequency, probably they do, because we have different voices, right? And each of us, of course it can overlap, but each of us has a different property, different frequency most of the time. So you can actually separate them. But in the time domain, no, you cannot really separate them. So for the formula, as I told you in the beginning, most of the time this is not called W, of course, it's an omega, it's a Greek letter. And as I told you, W is 2pf, but you can of course say W, people would understand. Okay, so let's continue with the next steps. So let's talk a bit more about the coding and compressions with a better writing, this time better sketches and so on. So yeah, we have the input, let's say an image of monkey, right? We have the FFT step, so we fast Fourier transform the image. Or in JPEG compression specifically, it's discrete cosine transform, DCT. But FFT has the same logic as I told you before. Then we have a step like entropy coding. It usually looks something like this. And then we have the inverse Fourier transform to have the image back, but this image this time is a compressed version, so it has a smaller data size than this one. Okay, so we will now consider the entropy coding part a little more. So we will see the limits. How can we not lose any information? The logic I explained to you a couple of minutes ago was a lossy compression. So we canceled out some of the pixels or some of the values that are close to the zero. But in this one, let's see if we can somehow compress data, somehow code the data without losing any information. So yeah, let's talk about entropy coding. Let's say you are the source and you're sending some messages to the receiver, right? And you send either of A, B, C, or D, okay? And of course, you cannot use the letters. You need to send your message using bits, right? And let's say 0 represents A, and 10 represents B, 110 represents C, 111 represents D, right? So let's calculate the average length of the bits, right? When we calculate it, we will see that average bits per symbol is 2.25 bits. How? So, by the way, let's consider that all of those occurring are the same probability, so like 1/4, right? We have 4 events. Let's say 1/4 is their probability distribution for each of them, probability, and this is the uniform probability distribution. So when you look at it, 1 bit, 2 bit, 3 bit, and 3 bit, so when you look at the average length per average bit per symbol, it's 2.25, right? So I'm wondering, can we do a better coding? Can we represent A, B, C, and D in a better way, without losing any information, let's say? So let's check the entropy of these representations. As I told you, it's like 1/4 each of the possibility. So P of X is 1/4, and logarithm to 1/4 is, in the end, you have this entropy value, which is 2 bit per symbol, okay? So you can see that the length is a bit more than the entropy itself. So it actually tells us that we can make something better, right? Let's say we did this. So instead of coding it with only a 0 and then using 3 bits for C and D, like in this one, we can just use this type of a coding. So we can represent each of the letter with 2 bits, right? And what happens in this scenario? Average length is now 2 bits per symbol. And entropy is again 2-bit. So when you look at the average length, of course, it's like for each of them 1/4. Each of them are 2 bits, and there are 4 of them, so it's 2 bits per symbol. Entropy is the same. Can we do better? No. Why? Because we have the limit. We reached the limit, which is the length we represent, the like bit per symbol length cannot be smaller than the entropy. So we reached the limit. So yeah, that's basically the logic behind entropy coding. I hope you understood well. And in the next session, I will talk about SVMs and kernels. You don't have to watch that part. So if you want to read the paper or review the paper with me, the paper is mainly about information theory, as I told you in the beginning. But to better understand the paper, I would suggest you to watch something about SVMs and kernels. It would help you understanding the paper better, but you don't need that, so you can pass this part. Hello everybody, hello again. So let's continue with SVMs. And yeah, this is the general schema for SVMs. Let's say we have some round shapes and we have some triangles we want to classify. We want to separate them, right? And this one over here is called the hyperplane. So SVMs are also called hyperplane classifiers. Okay, so this is called the margin of our hyperplane, right? So we want to maximize them. And for example, for our margin, only these points are defining our margin, right? Only these and these points are defining our margin. This doesn't define anything, okay? This doesn't define anything. Okay, let's delete them. So whatever you do with those, for example, or those, doesn't affect the margin, but when you change change these values or change these data points, the margin would also change. That's why we call them support vectors. Okay, support vectors. Okay, the same for this one. Let's say SV. And SVMs are support vector machines. Okay, so what is the math behind it? How can we define the margin? How can we maximize the margin? I will tell you in a second. So to begin with, I will just create a vector perpendicular to the hyperplane. It will make things easier, okay? So let's say this is perpendicular. And for any point that is on the hyperplane or that is on 8, 0, right? When you take the dot product of, let's maybe make it a bit bigger. Yeah, let's make it 10. And let's show it again. For any vector or any point in 8, 0, when you take their, let's say this is W vector, okay? And let's say this is X vector. Whenever you take the dot product of them, no matter which one, let's say another one over here, no matter which one, it is equal to this value, right? So let's maybe write it down. W vector times the X vectors, no matter which of them, of course divided by the magnitude of the V equals to C, right? So we will see something from here. Okay, let me show you with another color. If we multiply both of the parts with W magnitude, right, and these goes away, this value over here is actually just a scalar value, right? Why? Because C, which we called it here, C is a scalar value, let's say like 5, 10, something like that. And the magnitude of the V is also a scalar value, right? Let's say 7, something like that, right? It's a scalar value too. Okay, so we can give it a scalar value, let's say minus B for mathematical beauty. I will show you in a second. Okay, so what we have on our hands in the end is W times X equals minus b. If we push it there, w times x plus b equals 0. Maybe it looks similar to you from neural networks. And this is called hyperplane equation. Hyperplane equation in SVMs. Okay? So yeah, keep in mind this one. And for the data points, let's say one data point is over there, right? One data point is over there. What we would say is w times x plus b is greater than or equal to 0 for the ones here, right? And for the ones here, w times x plus b smaller or equal to 0, right? Okay, so also for this one and this one, we can identify them using basic analytical geometry. Let me take another color. Okay, so maybe we can delete this ones. I already shown you how it comes, right? This is the hyperplane equation. For this one, let's say w again, of course, times x plus b equals to k, right? The value here. And here, w times x again plus b equals minus k, let's say. And for just mathematical simplicity, let's call them 1, but we know them. We know that they are like scalars or floating points. Okay, so we have the h1 and h2 equations also. And this one is the hyperplane equation. 0 equals to 1 equals to minus 1. Okay? Let's delete them and make them their simple version. Okay, now what I will show you is something really crazy, guys. Let me delete these for simplicity, maybe. Right? Okay. So, what I will show you is something interesting. Okay, or maybe let's take something else. Done. Okay, so let's choose x minus, right? X minus, let's say. And another one here, let's say x plus, right? Because I want to look at the margin, what is here. That's an optimization problem, guys. If there's an optimization problem, and if we want to maximize the margin over here, we need to know the margin. So to know the margin, we will use a trick, okay? Yeah, x minus, x plus. A positive sample and negative sample we chose, or two different classes, right? And when you just turn it back, so minus x minus it becomes, right? And when you look at the result, it's something like this. It doesn't need to be perpendicular, by the way. It doesn't need to be. So let's, okay, yeah, let's delete this ones again. Okay, so it doesn't need to be perpendicular. So let's maybe, what we did so far is x plus minus x minus, right? We took it. This is this value. So, okay, we know this value is equal to x plus minus x minus, right? Times the w vector divided by the magnitude of it, the normalized version. So it equals to the margin. We need to know what we need to maximize, right? So yeah, how do we find x plus and x minus? We already have them actually. X plus is coming from here, plus, and x minus is coming from here. If we put them to their place, what we would have is, okay, x plus times w minus x minus times w, right? Because I just did this. Okay. And we already know this value, which is 1 minus b minus, and this one is minus 1 minus b, okay? And if you open it up, it is equal to 2, right? This becomes plus, it goes. This becomes plus, and it's 2. We also had this value over here, so let's write it down before finalizing it. Okay, so that's it. That's our margin, right? Margin, simplified margin. So instead of maximizing it, mathematicians just wanted to do something different, but it is intuitionally so basic. They wanted to, instead of, or let's just write not maximize, but instead minimize this one, okay? So yeah, we have this one over here. We want to minimize it, right? And we have some constraints that are these. This one, or more precisely, these ones, right? More precisely, these ones. This must be, let's write down the constraint also. V times x plus b should be greater than 1. V times x plus b should be smaller than minus 1, right? And this one is for the positive values. Y equals 1, let's say, positives. And this one is for negatives. Y equals minus 1. Let's change the color. So yeah, these are the constraints. And this is the objective function. We want to minimize it. Objective function. Let's make it more beautiful, okay? When you look at it, like, instead of having two different equations, we can have only one single equation, right? And to do that, what we can do is, look at it. Just y equals to 1, and then it becomes bigger than plus 1. And when it is negative, it's smaller than minus 1. So when you actually multiply it, it would become, of course, it would change, and it would become plus 1 too. So what you can say is y multiplied by vx plus b is always greater than or equal to 1. No matter if it's positive or if it's negative, because when it's negative, this is the equation, and when it is positive, this is the equation. So no matter what y is, or we have this constraint. So instead of having two different like equations, or inequality, not equation, but inequality, let's say, we can have only one, right? With some simplifications. Okay, this is our constraint, and this is our objective. And here is the Lagrangian multiplier function. I will show you in a second. It's an optimization problem, and when it's a constraint optimization problem, we can solve it with Lagrangian method. Okay, so let's write down the Lagrange equation. If you have no idea about what is Lagrange equations and what is constraint optimization, don't worry. It's just a technique used in constraint optimization, and I will put some links below in the description so that you can have more idea about what is it. But if you don't have any idea, you can continue watching even, don't worry. Okay, let's write down this one, because it's the function we will minimize, right? And this is our constraint. So let's write down this in a more beautiful way. Okay. And then, what is our constraint? We usually write it down like this in Lagrangian equation. And then let's put it there and then write it down. So what do we have? We also have some indexes because of the sigma, right? wi xi plus b minus 1. And yeah, that should be it. Okay, and the next step of Lagrangian multipliers is taking the derivative, partial derivative of each of the variable. Okay, So when you do this, what you would have is W minus sigma alpha I yi xi, right? Yep, yi xi, since this is a vector. Okay, so let's make it 0. And if I make it 0, what I would see is the W vector is actually equal to the sigma alpha I yi xi. Nice. Then let's take the partial derivative of, the bias, or the B. And when you do that, you see there's this one over here. And when you take the partial derivative, what you would have is alpha I yi and equals to 0. Okay. So when you put them to their places, what you would have, I won't show you in detail, but you can also try at home or with a pen and paper, you can try it. What you would have is L equals minus sigma alpha I minus 1 over 2 sigma sigma. This one is for I, this one is for Y, you will see Y, alpha I alpha J, and yi yj, and xi xj. These are the vectors, and the most important part is here. You see, for the data points, there's a dot product, right? There's a dot product. That's really important. So we can see that we can solve the Lagrangian equation using the dot product. We can see the relations of different data points, and it exists in the dot product, right? And there's a dot product existing, let's say. Okay, so if your data is linearly separable, like in this one, let me show you with a magic pen, like in this one, no problem. But what if you cannot solve it, like you cannot linearly separate your data? Here is the kernel trick comes into play, kernel trick. Okay, so a kernel is a mapping function kind of. So if it's not linearly separable, you can just make the dimensions, change the dimensions, or project the values in a different dimension, a higher dimension. And for example, let's give a quick example, right? These doesn't seem linearly separable, let's say, in 2D, not linearly separable, separable. But if you convert these values to a higher space, let's say one kind of an polynomial kernel, right? What you would see is the following. So again, we didn't touch those ones. There is darker blue, and we touched the ones with the lighter blue. So if you look from the Z direction, these are only in this, let's say X and Y plane, but those are in the Z, that those also have the Z value, so they are upper, right? So with a hyperplane now, let's say with a hyperplane now, that cuts here, let's say, hop, you can linearly separate them. Okay, maybe it's not really understandable from this drawing, but hopefully you understood the point. If you make them go to a higher dimension, and if you can separate them, it's fine. But what if you need a lot of dimensions? Would you still project all your data to a higher dimension? No, there's a trick instead of doing this. So you remember I told you about the dot product, right? The dot product. So instead of converting them to a higher dimension, since the important part is their dot product, you just, instead of converting them or like transferring them, mapping them to a higher dimension, just calculate the dot product in a higher dimension. That's the logic of kernel trick, okay? One quick example. Let's say our transformation function phi x is just this one, okay? X1 square. As I told you, it's like let's say we converted it to a bigger dimension, our data, right? And square root of 2 x1 x2, right? And let's say our data point x1 is very basically 1 and 2. This is the x1 value of x1, x2 value of x1, right? And let's say our data point x2 is let's say 3 and 4, right? This is the x1 of x2 and this is the x2 of x2. So let's calculate the dot product in the beginning, right? x1 times x2 equals, okay, the first terms and the second terms, and then add them together. 1 times 3 plus 2 times 4 equals 11, right? Okay, let's keep it. And let's find their transformed values, right? So for phi x1, it would be the square of 1, which is 1, then the square of 2, the x2 of x1. So what it would be is 4, or to the power of 2, let's say, and then times 1 times 2, which is basically 1, 4, and 2 square root of 2, right? Okay, it's not really seeable. Let's make it a bit smaller. 1, 4, and 2 square root of 2. Okay, and then what is your phi x2 is, take the square root of this one, square of this one, 3 to the power of 2, 4 to the power of 2, and then square root of 2 times 3 times 4, and which you would have 9, 16, and 12 square root of 2. Okay, then you have phi x1 and phi x2. So what you can do is just finding their dot product in this dimension, and after a lot of calculations, a lot of calculations, you would end up with 121. Okay, you would end up with 121. Instead of doing that, what you can do is doing that kind of a projection only in the dot products. Okay, so let's say we have a kernel function x, and or kernel function x1 x2, and let's define it as x1 times x2 square, which is a polynomial kernel, by the way. It's a famous polynomial kernel function. Okay, and instead of doing all these calculations with this kind of a function, you would find, we already found, do you remember we already found x1 times x2? You can easily find its square, which is 121. If you don't believe me that this product is 121, please check. But yeah, it is 121. It looks magical, but yeah, it's not. So basically, instead of defining like quadratic projection like this, then calculating both of their projections, then calculating the dot product of the projections is too much work, and it conquers a lot of memory. Okay, it has a lot of memory, and instead of doing that more effectively, we have just a kernel function, right, which is a polynomial kernel. And since you only care about the dot products, you can see here in our equation you only see the dot products here. So what you can do is just taking their dot product with a polynomial kernel and then square it. Okay, and you have the same results. Okay, so I hope it was clear, and in the next part we will talk about GMMs, and which means Gaussian multivariate mixtures or Gaussian mixture models. So yeah, let's continue with GMMs or Gaussian mixture models, right? You're probably already familiar with what is k-means, right? In k-means, okay, both of them are like how do you say, clustering algorithms, but in k-means we give hard labels to the data points. For example, this one is only from the blue class or blue cluster. This one is only from the green cluster. But in GMMs, we give somehow a Gaussian distribution to each data point instead of a hard label. Okay, so for example, this one's over here. This is also from the blue distribution and also from the red distribution, right? We don't have like hard labels like blue or yellow, something like that. No. Okay, so what is the math behind it? Let's continue with the math behind it. So the probability of each data point is equal to the sum of from k equals 1 to n, the nth Gaussian distribution, by the way, pk, let's say, times the normal distribution of x given the mean value mu k and the covariance matrix x, like sigma k, let's say. So it would be normally a variance, right, in a normal distribution, but it's a multivariate Gaussian distribution, so it's a covariance. So instead of a single Gaussian, you also have like elliptic behavior thanks to that covariance matrix. Okay. Yeah, as I told you, these are like somehow Gaussian distributions fit over data here, something like that. Okay. When you think like in 3D. Okay, so what is this formula? This is the weight of the kth Gaussian distribution. Okay, and this is the multivariate normal or Gaussian normal distribution. Okay, so yeah, we calculate the probability of a single data point with this formula. So we have, during the training of this algorithm, we have a step called expectation and maximization. Okay, expectation and maximization. So at expectation step, which is the first one, okay, the first step is you calculate gamma, which is the probability sample ith belongs to Gaussian kth. Okay, so you you just calculate the expectation of single samples, right? Then the maximization step is the second one. You update the weights which we shown here in this formula, right? Update the weights. Means of each Gaussian. For example, this one is the mean of some of them here. There is a mean over here. There's a mean over here for this one, right? You update the mean values for means for the Gaussian distributions, and you also update the covariances, right? This one over here, covariances. How do you do that? So quickly looking at the formulas of them, very quickly, guys. So you kind of continue these two steps until the first one doesn't change much. Okay, you calculate the gamma, the probability sample ith belongs to the Gaussian kth. So each of the data points belongs to, let's say, green one, and then you calculate another data point that it belongs to the blue one, that it belongs to the red one, but it doesn't change much after a while. Then it means it converged, so you don't update anymore. Okay, so let's look at the formula of this gamma ik equals pk, which is the weight, right? And then normal distribution xi mu k and the covariance k divided by the sum of j equals 1 to nth Gaussian distribution, the weighted sum of other Gaussian distributions, right? And xi mu j and okay, so what we have here is the weighted sum, and we calculated it for the single of them, right? Single Gaussian of them, the kth one, let's say, and then we divided for the we divided by the weighted sum, and we calculate the gamma, the probability sample ith belongs to the Gaussian kth. Okay, and then after calculating this, we update three variables: weights, means, and covariances. So the weights is updated via this function from I1 to n, right? And you have the gamma ik divided by n. So this is the average of probabilities. Okay, and after calculating that, you also calculate the mu k, the new mean values, right? So from I equals n to I equals 1 to n, sorry, then the gamma I k x I divided by the sum from I equals 1 to n gamma I chi. So what you have here is the weighted average of all possibilities, right? Or of all points. Weighted average of all points is your new mean value. And finally, you also update the variance or covariance matrices, right? From I equals 1 to n, the gamma ik xi minus mu k, which is basically the variance, divided by the sigma again from 1 to n gamma ik. So what is this? Again, the weighted variances of all points. So yeah, finally we have all the foundations required to read this intimidating, the 50 pages long NeurIPS paper, right? Yeah, don't worry about it. Okay, it looks really intimidating and scary at first sight, but we have all the foundations required. Yeah, the notations are intimidating. There are many figures, propositions, definitions, but don't worry, we will explain one by one, and at the end of the video you will able to read and understand the NeurIPS paper. So as a quick summary, first of all, of what we did, kernel is a function that defines a relationship or a transformation, right? No problem here. As I've shown you in the SVM part, maybe you can remember that. We can like project a lower dimensional data to a higher dimensional data with a kernel. But kernel function, more specifically, is enabling you to use the kernel trick, and it's used to compute similarity between data points. So it's a function that computes the dot product, right? And Markov kernel specifically is another projection function, and it's mapping points to conditional probability distributions. Okay, it's not like mapping the points to a higher dimensional space deterministically. No, there's also a probability involved. So in this paper, Markov kernel is used, and specifically Gaussian mixture models, which I've already shown you, is used, because if you think of it, it's actually doing the same thing, using mapping points to conditional probability distributions, right? It was not like giving hard labels, like in a normal kernel function. Perfect. So let's start the paper. When is an embedder more promising than another? First of all, we need to know what is embedder, right? Maybe you already know, or you already have ideas about it. As I told you, okay, it's a NeurIPS paper. So what is an embedder or embedding models? Let's say we have any type of a data, right? A textual data, a voice record, or a video, right? No problem. You somehow code it, okay? Just like I've shown you in the JPEG compression part, you code it or you squeeze it in a lower dimension, squeeze it and turn it into a vector, okay? So if an embedder model is good enough, so you would convert your data to vectors without losing any information, or losing some information but as low as possible, okay? So what do you use them afterwards? How do you use them afterwards? So let's say you have many, don't look at the voice record and video for now. Let's say you have many data, many textual data, let's say many PDFs, okay? And then you want to look at one single part in those all PDFs you have, right? So you give a quick sentence, let's say the war between Ukraine and Russia, right? And the embedding model is just, you make a search kind of, right? The embedding model has already embedded all the data. You have all the PDFs you have. They are already vectors. And then your query is at another vector, and you do kind of a semantic search. You look at the cosine similarity between your query, the war between Russia and Ukraine, and all of your PDFs. So in any of your PDFs, any paragraph or any PDF, it depends on what you embedded, right? And then chooses the most similar one. Okay, that's the idea of embedding models, but it can be images as well. So I converted my face to a vector, right? And let's say someone else, let's say Alex has converted his face to a vector too with the same embedding model, let's say, or some other embedding models, and we can calculate the similarity between our faces. Another use case. It's used in almost everywhere. It's used in classification tasks also. How? So you have data again, let's say MNIST data, maybe you're familiar with MNIST data, and then you add just fully connected layers after your embedding model, right? And then you can use those embeddings as a classifier, right? With the help of some fully connected layers. Whatever. Yeah, embedding models are just converting some data to a numerical representation, okay? And it's so similar to what we are doing in information theory in general. We are trying to encode data, right? So we can use the information theory concepts in embedding models, and that's what exactly is done by the authors of this paper. Okay, so the motivation of this paper is embedding models transform data into numerical representations, as we already said. And choosing the best embedding model or best embedder is challenging because you always try to like rank them. Let's say you have model A and model B. How do you define which is better? Is you choose a task, let's say classification, and then you compute their performance on that specific downstream task or specific task, right? Instead of doing that, and as I told you already, like you can do it in any data modality or any data type. So instead of doing that, let's create a metric. That's the motivation of the paper, right? So the general figure of the paper, let's say you have concepts or the labels, we can say, right? Which is shown by probability of y given x, and x is the features of your data, okay? Which is basically your data, your images, right? Your images. And let's say the concepts are your ages of people in those images, right? So let's say you embed your images with embedder U and with embedder V. And after you created the vectors, you embedded the images, and then you can simulate the U embeddings. You can use those vectors and then simulate them. It can be anything. It can be a kernel, for example. You use those vectors and you map those vectors to another vectors, and then you try to imitate the V embeddings, right? So if you can do that, you would say that U is sufficient for V. I will explain you in a second. But yeah, that's the main idea of the paper. They are checking if U is better or V is better, looking at, okay, there are the embeddings, or there are the like vectors created by the embedder U, and can you use those vectors to simulate V, or can you create V from the vectors from U, or the embeddings from U? That's the paper, actually. Yeah, this small figure explains the whole idea of the paper. But of course, we will get more deeper. So to start with the first definition, sufficiency. Do you remember, guys? If you don't remember, please roll back and listen that part about sufficiency. It's quite related to what is sufficiency in like core information theory or basic information theory. So U is sufficient for V if you can find a Markov kernel, or a kernel that takes the embeddings of embeddings of U, which is shown as P U given X, okay? Embeddings of U, and then you convert it to another place, and then you subtract the embeddings of V, and you look at the total variation distance. Do you remember also TVD? It can be Kyle divergence as well. And if it's 0, the expectation is the average, or the weighted average, right? And if it's 0, we can say that V can be simulated from U using M without information loss. This is called sufficiency, okay? So you take the embeddings from U, you map them with a Markov kernel, which is shown as M here. You project them to another space, and then when in that another space, they're exactly matching with V, right? And the variational distance, or the Gaussian distribution distance, is 0. There's no difference. So we can say that U is sufficient for V. And also, more informativeness is, do you also remember this formula, the mutual information formula? So PU given X is said to be more informative or less noisy than PV, or the embedder V, if and only if the embedding models always satisfy the inequality. So you have Y and U, and the information of Y and U is bigger than the information of Y and V mutually. Okay, but sufficiency is a more important term in this definition. But I hope this is also clear. So one proposition by the authors or the relationship of sufficiency and information is, if it's more sufficient, then it's more informative. So if you can create, let's go back. If you can create the V embeddings from U embeddings with just a Markov kernel, you can say that U is more informative than V. It has more information because U can perfectly simulate V. Right? Sorry. So, but the reverse is not true. So if it's more informative, you cannot say that it's more sufficient. I will tell you in a second. I mean, the paper authors will tell you in a second. But one thing, that if it's more informative, then we can give this as this formula. Okay, you also know what is Kyle divergence, right? It's again the same thing. Looking at the Gaussian similarity between this Gaussian distribution and this Gaussian distribution. Same for this one. Looking at the Gaussian distribution, like difference between this and this. So it tells that between two concepts, let's say age group 5 and age group 10, when you look at let's say you have the data, right? And you converted them to embeddings. And for two different concepts, age group 5 and age group 10, the Kyle divergence of those groups are more different in U embeddings. Because there's too much information. Intuitively, of course, there's a proof of this, mathematical proof of it. But intuitively, let's say age group 5 and age group 10, they have a lot of difference in one embedder model. And in another embedder model, 5 and 10 are not that different. So we can say that the vector representations are not giving you enough information intuitively, right? So yeah, that's the other, like the second part of their first proposition, right? Okay, a remark is, as I told you, although U being more informative than V doesn't necessarily imply that U is more sufficient than V, and there's a proof of it in the paper also, but intuitively, okay, we can say that U is more sufficient than V if we can like perfectly recreate V from U. But if you just look at the mutual information, you cannot say that, okay, if I mean, maybe they are really different, Y and U are maybe really different, so even though Y has more information than V, it doesn't mean that V can or U can recreate V, okay? So, okay, if it's more sufficient, then it's more informative because U already has everything we have, right? Or has. But for informativeness, even though one of them has more concepts, more conceptual differences, like in this formula, it doesn't necessarily imply that it can perfectly simulate the other one, okay? So the second proposition here, they also wanted to look at it from the Bayesian risk perspective. So what you can say, just look at the second one. Maybe the first one is not that crucial. So if U is how do you say, sufficient for V, right? If U is sufficient for V, what we can say is the Bayesian risk is smaller. So the probability of your model making mistake, like making a guess that is not actually, for example, the image was 15 years old and it said 50 years old to the image, is smaller than V making mistake. So V would V would make more mistakes because it's less sufficient. Like U is more informative, let's say, than V, or sufficient for V. So we would say that, I mean, there is a smaller risk that U makes a mistake. Okay, so until now, what we saw that either U can be simulated by V or V can be simulated by U, like they can simulate each other. This is called equivalence, so they can simulate each other. And comparability is U can simulate V, but V cannot simulate U. So far we only considered equivalence and comparability, right? But what if they're non-comparable? So U cannot sufficiently create V, or U is not sufficient for V, and V is not sufficient for U. What do you do in this situation, right? Not by the paper authors, but by Lecam, which wrote a paper in 1963 and addressed this issue and called it deficiency, okay? So, okay, this was already written in proposition 1, but as I told you, it was equal to 0. The total variation distance was equal to 0, right? But it doesn't need to be. What if these are not comparable? In this scenario, you just look at the infimum. If you don't know what is infimum, you can consider it as the minimum, okay? I will give you a basic example to the description, but infimum is basically the minimum, let's say, or the maximum of minimums, but no problem. Looking at the worst case scenario. Okay, so sorry again. So you map the U embedders, or map the U vectors, and then you simulate V with this operation. By the way, this M is used as Gaussian mixture models, multivariate Gaussian mixture models in this example, and called Markov kernel in the paper. That's why I told you about the kernels and Gaussian mixture models. Okay, so what was the main idea of Gaussian mixture models is to set the data points, transfer the data points to conditional probabilities, right? So you take the vectors, and since it's so challenging, the dimensions are too high, you cannot deterministically map them to V. You can like in a probabilistic way, you can map them to V, and then you look at the total variation distance, and deficiency is the minimum the minimum value you have from here. So the kind of worst case scenario, actually, not minimum is not the right word for here, but okay, you're not making it you're not expecting it to be zero, not like in the proposition 1, right? You just look at the total variation, you take the infimum, and it's your deficiency. Okay, maybe you cannot perfectly simulate from U, but you can be close enough. So that quantity is called deficiency, which was addressed by Lee Kem in 1963. So the main contribution of the paper, what the paper did is, okay, they already explained the background, right? So those are not really from the paper. These are just from the background. Only the 8th slide here, the main contribution, is from the paper. So instead of looking at the deficiency, they calculate something more basic, more traceable, they say. So there's the uncertainty of V. So uncertainty and entropy and information, they're all directly related, or directly there's a direct relationship, let's say. So you look at the uncertainty of V, so the information V has, minus the uncertainty when simulating V from U with M. M is again a Markov kernel, a Gaussian mixture models, okay? So you simulate V from U with M. So you look at how many information left, like how small or big, I don't know, information left when you simulated V from U, the big like embedder, let's say. Why do you have this uncertainty of V? Because just imagine a scenario, you're comparing one really strong model with a weak model, and then you compare it with a really strong model, and then a strong model, okay? If you wouldn't have this uncertainty of V, let's say, if you only looked at this one, so you would put the strong model and weak model at the same class, because as I told you, if you're comparing it with a really strong model, since you don't have this, let's say, I mean, this very strong model has can already like simulate V from U, so that's why you also have the uncertainty information of the model you're comparing with, okay, so that you rank fairly. Just think of it, guys, like this is the information from V, and this is the information left, kind of. That's the main contribution of this paper. Okay, so let's go to the results. So when you rank them in downstream tasks, let's say classification, let's say information sufficiency, but by the way, the main contribution is called information sufficiency by the authors, right? So when you rank them in downstream tasks, let's say classification, clustering, something like that, and if UAE large V1 is let's say number 4 in downstream tasks, and in information sufficiency rank, it's also number 4, number 5, number 6, something like that. So there's a linear correlation, there's a direct correlation which is clearly seenable from the graph. So what they can say is there's a high Spearman correlation between the information sufficiency ranking and the downstream task ranking. So what you can say is, okay, we can definitely say information sufficiency and downstream task accuracy, or the ability of the model, is correlated. So information sufficiency works as a good metric, right? And when they actually create the big model, and these are like model like different embedders here, and then the same thing applies here, different type of embedder models. So let's say gamma here and gamma here, let's say ChatGPT here and ChatGPT in the same direction. And what you can see here is groupings, right? There's one group, there's a big group here. And when you create the information sufficiency maps in a different way, you also see some like groupings here, and for example, this grouping here can be seen here. And more importantly, in the paper, they report that if there's a grouping, if the information sufficiencies are similar to each other, then those models are trained the same way. So if one of them is trained with diffusion, let's say, or trained with, let's say, GAN kind of expectation, minimization, maximization method, let's say I just made it up, they group together. So information sufficiency is actually working in another way, right, we can say. And as I already shown you in a different setting, again, there's a kind of a linear, how do you say, correlation or linear increase, right? And this is also an interesting graph. So let's say you have gamma 2b, and then you fine-tune it with Italian language. The classification accuracy increases, and when classification accuracy increases, the information sufficiency also increases. So yeah, nice. We read and understood the NeurIPS paper. So how to write this article at home? I assume now, if you watch the video closely enough, and if I was able to explain it well, now you're well versed in the concepts of information theory. You know the information theory concepts. And after all, embedding models are also encoding information, right? These are also like closely related to the concepts in information theory, embedded models or embedding models. I can apply, or you can apply, the concepts of information theory to embedding models, right? Are there any missing pieces or research gaps in the field? Yes. For example, we compare, as I told you in the beginning, the motivation of the paper is we compare the embedded models in downstream tasks, right? So yes, there is one research gap, and you can develop a metric solving this issue. I hope everything was fine. Please write down in the comments, and you can ask me any questions. I will try to answer as soon as possible via email or via like just writing down as a comment. Comments would be more appreciated, to be honest, because others can see your questions and benefit from it too. So see you guys. Thank you so much for watching.